Were there any questions from last time? So last time we talked about the chromology of the symplectic quotient. So G was a compact connected Lie group, and M omega was the symplectic manifold. Phi was the moment map, so you should assume that either M is compact or the moment map is proper, or something like that. G is acting freely on phi inverse of 0, and M red is the symplectic quotient, and then there's this diagram. So the diagram starts with the equivariant cohomology of M, and then there's a restriction map to the zero level set. I can just pull back equivariant forms under the inclusion of phi inverse of 0 and M. And then this vertical map is the isomorphism, so it's just descending to the quotient. And the composition of these maps is called the Kirwan map, so I'm calling that K. And the theorem is that that's surjective. And there's also this inclusion of invariant polynomials on G into the equivariant cohomology. And so there's a natural map from invariant polynomials, which is the characteristic class map. So you have this bundle over the symplectic quotient, which is the zero level set. And so if I take some curvature two form and I take some invariant polynomial applied to that two form, then Chern-Weil theory says that I get a well-defined cohomology class, which is independent of the choice connection. So the bottom horizontal map is I just plug the curvature into the polynomial. And then this diagram.
There's a question in the chat.
Yeah. Yeah. So it's enough for the moment map to be proper. So I'll use some non-compact examples. You know, a lot of times this is stated as a you know, in the context of compact manifolds, but you can allow certain kinds of non-compactness as well, as long as you're careful. Any other questions? Right, M doesn't necessarily have to be compact. Although every time you have a non-compact example, you sort of have to check that it's okay in that example. Okay, so what's a particular non-compact example that works? So an example would be M is Cn, and Gx on S1 scalar multiplication on each factor in Cn. And so then M red is Cpn minus 1, complex projective space. And so what are each of the terms in the diagram in this case? Well, the polynomials on G that are G invariant, G is just acting trivially on the algebra in this case because the group is abelian. So this is a polynomial ring in a single variable. And HGM is the same thing. So because M is equivariantly contractible to a point, that contraction induces an isomorphism in equivariant cohomology, and the equivariant cohomology of a point is just the invariant polynomial. Okay, on the other hand, we know what the cohomology of projective space is. It's generated by a single class. Usually that class is called H, the hyperplane class, and the relation is that H to the n is 0. And so the same thing up here, that this equivariant cohomology of the 0 level set is isomorphic to the quotient. So this is also the truncated polynomial. And so what does this map do? Well, you have T over here, and you have the hyperplane class over here, and T maps to H under this map. So this is another way of saying that the hyperplane class is plus or minus the. It depends on your conventions. The first term class of the hyperplane bundle, or the tautological bundle, if you allow to reverse the sign. Okay, so the kernel of the quantum Kirwan map, in particular, is this T to the n ideal generated by T to the n. So let's make one addendum. This is addendum C to the Meyer-Marsden-Weinstein theorem. Which is that suppose that the J on M is integrable. And and the G action extends to the complexified group GC. So the complexified group is the group whose Lie algebra is the complexification of Lie algebra V. And so then you can define the semi-stable locus to be the image of the 0 level set under multiplication by the complexified Lie group. And so then the quotient of the semi-stable locus by this action, this is just another way of defining the symplectic quotient. And this semi-stable locus is open and dense if non-empty. So in this example where I take M to be Cn, and the moment map said was the sum of the zj squareds over 2 minus some constant. Then the semi-stable locus in this case, I mean, the zero level set is the sphere. That's 2n minus 1 sitting inside Cn. And the complexified group here, so G is S1, so GC is the C star action. And so the semi-stable locus is Cn minus 0. And so then another way of describing the symplectic quotient is that it's Cn minus 0 divided by C star. So that's of course just another description of complex projective space. And this addendum is, for example, in Kirwan's thesis. Okay. So our goal is to extend the Kirwan map to quantum chromology. So we want to map QK, which goes from QHD to QH and then. And so I have to talk about what do we mean by quantum chromology. And let me first say I'm not responsible for the terminology quantum chromology. So I think Nuno's course is about quantization of vortices. This is a different kind of quantization, where you view quantum effect as coming from a holomorphic curve. Okay, so now M omega can just be any symplectic manifold. And again, sometimes you can make it work in the non-compact setting, but let's just say it's compact. And J is the compatible almost complex structure. And so then we take a complex curve. And so then it has a little j. J squared is minus identity. Here, the big J squared is minus identity on Tm. And map from C to M is pseudo-holomorphic. If and only if its differential is complex linear on each EZC. So what does that mean? That means that if I take du and evaluate it at z, and then take j, u of z, this should be the same thing as du of z composed with little j and z. So this is some equation which is in the context of symplectic manifolds introduced by Romão. And now let's suppose I have cycles Z1 up to ZK representing a basis. For H of M, and I want to be a little bit vague about what I mean by cycles. I mean, for the purposes of this discussion, let's just assume that they're submanifold. And then let's suppose I have cycles representing a dual basis. And let's assume I have a homology class in M. And then I define the structure coefficients of the quantum product. This is a signed count of the number of maps from P1 to M of class beta, such that U of 0 is in Zi, U of 1 is in Zj, and U of infinity is in Zk dual. And of course, this should be pseudo-holomorphic. So this is in general position. That means that you might have to perturb the cycles so that the intersections are transverse, and you define to be 0 if the number is infinite. And there was a question about modding up by the automorphisms of P1. So here I'm just looking at the 3-point Romão-Houghton invariance. So I'm looking at P1 with 3 markings on it, and so in that case there are no automorphisms. In general, the definition would involve defining the modular space of stable maps by looking at maps of, say, arbitrary genus with arbitrary numbers of markings, and then you would mod up by the automorphism and take a similar count. So I'm just simplifying to a case where I don't have to worry about automorphism. Any other questions so far? So now you take Q to be a formal variable. Corresponding to a basis of each 2 of them. I'm not going to write out what that means. I just want expressions like Q to the beta to make sense. So this is some formal expression. So Q to the beta 1 plus beta 2 means Q to the beta 1, Q to the beta 2. And so now if I want to take the quantum product of Zi and Zj, it's the sum over homology classes beta and indices k and ijk of beta times Q to the beta times Zk. So this is called the small quantum product. And where does it define a product? Well, it defines a product on QH of M. In general, you have to use rational coefficients. And then also I took power series in these variables Q. And in good cases, the expansions that you get will be finite series in Q, but they have to be formal power series in general. Any more questions about the definition?
So you write Q are formal variables corresponding to the basis of H2M.
Yeah.
So why does that matter? A basis of H2M?
Well, there are different ways of writing this. Different power series rings that you can use here.
So beta is a basis element, maybe? Is that what you mean? Like beta 1 and beta 2, something like that? What is beta? Maybe that will clarify.
Beta was the homology
Okay.
class. So another way to say it is what is this Q? What is this formal power series ring? This is just a subset of the space of maps from HM to Z to Q. So I could think in terms of Fourier coefficients if I wanted to. If I think of Q as some function, but I'm only going to allow exponents which would take out, which lie in some lattice. And so then this expression Q to the beta is the delta function at this class beta. So it's the function which assigns 1 to the plus beta and 0 to everything else. And the structure on this ring is given by this law here. So the product of two delta functions is the convolution function. And so I'll get a delta function at a different value of beta.
Okay, there's also a question in the chat.
Yeah, it's yeah. So the quantum product now will go from QHM. Let's say times. So you could also do a tensor product there. To QHM. And the theorem is that it's a supercommutative. So it's commutative in the same sense that the usual cup product is commutative and an associative product. And let's do an example.
Hello.
Yeah, go
Hi,
ahead.
Chris. Yeah, so just one confusion. So this star is not the type of object that for a separate beta you define a star. I mean, you package all the betas and define a single star. Is that the case?
Yeah, you may be thinking of there's a more general definition, which
Okay.
depends on a choice of beta.
Okay.
So another thing I can do is I can take a gamma.
Okay.
Actually, any of the, it doesn't have to be a degree 2 chromology class.
Okay.
And then I can define Zi star sub gamma Zj.
Yeah. Yeah.
And this will be Nijk gamma of beta.
Right.
Q to the beta. Where now these things, it's not just 3-point Gromov-Witten invariant. So now you want one of these to map to Zi, one of these to map to Zj, one of these to map to Zk dual. But now you have a whole bunch of extra points here.
Okay. I see.
Which you require to map to this
Okay.
gamma. And then you mod out by the number of gamma factorial. However many gammas you have mod out order of some permutation. And so this thing is called the big quantum product.
I see.
And it specializes to the small quantum product when this gamma is equal to 0. And,
I see.
And so this these star gammas is that they form a family of together with the product, they give a family. Sorry, the Euclidean Poincare pairing. They give a family of Frobenius algebras structures on the quantum chromology, not equivariant yet, just the quantum chromology of that. So it's the small product is part of this more general.
Okay. Got it. Thanks.
So so an example would be if I take M to be CPN minus 1. And so if I have a map from CP1 to CPN minus 1, then this is given by an n tuple of polynomials. Let's call them U1 twiddle up to UN twiddle of some degree D. In 2 variables. Let's call them Z and W. So CP1, I'm thinking of having homogeneous coordinates Z and W. And I take polynomials in these variables. This gives me the components of this map. Okay, so how do I see that? Well, the way that I see that is very closely related to vortices. So I think of CPN as the quotient. CPN minus 1 is the quotient of CN minus 0. This was the semi-stable locus. And now I have this map from CP1 to CPN minus 1. So I can pull back the bundle. This is a C star bundle. And this has to be O of minus D for some integer D. So what's O of D? So there's a classification of line bundles, or equivalently of C star bundles on CP1. So I think of CP1 as being given by two copies of C modulo the identification map Z goes to 1 over Z away from 0. And so then this O of D is the bundle with transition map Z to the minus D. So and it has sections. So I think of Z as the coordinate on the first factor. So the sections are the polynomials. Z to the Z to the D minus 1 W up to W to the D. Global sections. Okay, well, by definition, U lifts to a map U twiddle, which goes from O of minus D to Cn minus 0. And so I can think of U twiddle as a section of from O of minus D to Cn, which is just D n copies of the O of D after I dualize. And so it's given by an n-tuple of these sections, each of which is a homogeneous polynomial. Okay, so in particular, if D is 1, then U is given by an n-tuple of linear functions in Z and W. Okay, so in particular, you see if D is 1, then there's a unique U joining 2 points in CPN minus 1. So if I have 2 points here, then there's a unique line. Going through them, and I can also say have a hyperplane here. So this could be a CPN minus 2, and it's going to intersect that hyperplane in a unique point as well. Okay, so let's suppose that this is Zi and this is Zj, and the hyperplane is the Zk dual. So you notice here that the Zi and the Zj are the same cycle, but I said you have to take general position in order to define these numbers. So that's what I mean. Whatever cycles you start with, you have to take generic perturbation in order to get the right count. So then this picture tells you that in this case, Nijk of, well, it's a degree 1 map. So so the homology class beta will just be the homology class of the standard line in CPN minus 1. And so I just get 1 here. And that implies that when I take the quantum product of the point class with the point class, I'll get Q to the well, let's call this, let's just call this generator 1. So we trivialize H2 so that H2 of CPN minus 1 is isomorphic to Z. So this class goes to 1 under that isomorphism. So then I have to dualize the CPN minus 2. The dual of that is going to be the class of CP1. So this will be an example of the quantum product in CPN minus 1. Now you can also sort of move these around. So you can, if instead of the incoming ones, I want to think of Zi and Zj, I can also take the product with the CPN minus 2. And then this will be Q times the dual of a point, which the dual of a point is just the fundamental class, and that acts as the unit here. So usually I would just write this as Q. Now, CP, the point, I can also think of as the CPN minus 2 to the n minus first power. So there are no quantum corrections. For this product, you can see that the first quantum correction is the one that I drew on the previous page. Okay, so that means that CPN minus 2 to the nth power is a point times CPN minus 2, and so that's Q. So the quantum homology of CPN minus 1, it's generated by this single generator, the hyperplane class, and now I have a formal variable Q. Well, technically I have power series, but I don't really need power series in this case. And the single relation is that Hn minus Q is equal to 0. Any other questions about the quantum product? So we sort of know.
Sorry, Chris, maybe you could say something quickly about these signs. You say that it's a signed number of.
Yeah. So the signs are a little bit complicated. So these moduli spaces are oriented moduli spaces of maps. So another way to say what this number is that Nijk of beta. I call this moduli space M03 bar of M from a beta. And I can also write this as an integral in M03 bar. And I can pull back zeta I cup product with the pullback of zeta j and pull back zeta k dual. And then integrate. So what the orientation gives me is it gives me a fundamental class on the moduli space to use for integration. So yeah, so there's some orientations that are built in here, which tell me, I mean, the fundamental class on the manifold depends on the orientation. So it's appearing there, and then the orientation. I'm also on the previous slide when I said that. Where did I say this? I wanted these Z1 up through ZK to be representing a basis for HM. That means I'm really taking oriented cycles so that yeah, they represent homology classes. Does that make sense? So it's a little bit like I mean, keep in mind that the Nijk zeros. This is the classical cup product. Of these three cycles. So how do you define that? So now I'm just talking about constant maps. So I just take the intersection of Zi and Zj and Zk dual, and I take the signed number. But you know, what do the signs mean in this case? Well, it could be that that Zi intersects Zj looks like this, right? And then Zk dual looks like this. And then there would be two intersection points. One of them would occur with a plus sign, and one of them would occur with a minus sign. And so the intersection number of these two cycles would actually be 1 minus 1 equals 0, as you would expect, because you can move the cycle, one of the circled off of the other. And the intersection number is supposed to be independent of the deformation. Did that help at all? No. Yeah, so in any time you have these intersections, intersection sets inherit an orientation from the orientation on the moduli spaces and the orientations on the cycles. And so the points come with a plus or minus one, and you add up the points in the intersection with those signs.
Yes, I think it's clear that we had a problem here with the microphone. I could not answer your question.
Okay.
Sorry.
Yeah. Okay. I wasn't sure when this stopped. Okay, so okay, so now you can see what the general feature. So that's one remark, is that it's a deformation of the classical cup product. And as a result, in particular, if M has no holomorphic spheres, then the quantum product is just the same as the classical cup product. So in our motivating example, M is Cn, and this certainly has no holomorphic spheres. And so the quantum homology of M is just going to be the ordinary homology. Now I'm working over Q. And there's a variable here. And when I stick in the equivariant part, this certainly doesn't change. So I just get an ordinary polynomial for the quantum homology of Cn. And then on the other hand, we saw the quantum homology of the quotient Cpn minus 1. This was polynomials in H and Q with the relation Hn is equal to Q. Okay, so what we're looking for is a map which goes from polynomial ring to the polynomial ring modulo single generator. Okay. Okay, well, I was going to finally talk about vortices, but I only have 2 minutes, so maybe this is not enough time to stay with the definition of a symplectic vortex lens, and I'll just stop there.
We've been asking questions in the middle, so if you want, you can just take 10 more minutes and go up till, because it's supposed to be 50 plus 10.
Oh, okay. So maybe just a little preview of what I'll talk about next time. So we already saw today that if you have a map to the reduced space, then I can think about the pullback bundle. So in symplectic geometry, we think of the symplectic quotient as the quotient of the zero level set. So this is some G bundle. And so if I pull back this G bundle, then I get a bundle over C, and it has a connection. It has a connection because there's naturally a connection on phi inverse of 0, which is determined by the complex structure. So this determines for me horizontal subspace. So let's call this connection A, and it comes with a lift. So by definition, U lifts to a map from P to inverse of 0. So a gauged holomorphic map is a name for the kind of thing that I get from this construction. Let's say the bundle P is the pair A comma U, where A is a connection on P, and U is the holomorphic section of the bundle P times G M. So it is that. That means I take all of the P comma M's and I mod out by PGM is PM. And I'm going to denote by H G of CM the space of such pairs. So this condition that it's J holomorphic, I'll write like this. So next time I'll talk about, the moduli space of vortices is then the reduced space obtained from the space of H holomorphic maps, and then I want to use that to define the quantum Kirwan map. So I took 3 months. I'll stop there.
Let's thank the speaker. Any questions?
Any questions here?
Has a question. Ritvik asked, can you explain what is the covariant quantum cohomology? That's his question on chat.
Yeah, so it's defined in several different ways. It's difficult to define it without getting into technicalities. But the easiest way to say it is that I have this moduli space of stable maps of class beta, genus 0, and 3 markings. And I have the evaluation map. I can choose the parameterizations of these 3 markings so that I'm evaluating U1, U0, and U infinity. And one of the ways of defining the structure constant I wrote down is that you integrate over this modular space of map. F0, whatever, F1, whatever, F infinity of whatever dual. And this map works perfectly well in equivariant chromology as well. Okay, so each of these, this evaluation map induces a map in equivariant chromology. MQ2, the equivariant chromology of the moduli space. And then this integral will just be the standard integral. Now it's a little bit dishonest because there are a lot of technicalities involved in the definition, but that's the idea.
Yeah, hello, Chris. Just naively speaking, I wanted to ask in terms of counts, what are we counting? Are we counting curves which are invariant under G or something? Yeah, I mean, that kind of interpretation I was looking for. I mean,
Oh, yeah.
that
It's more complicated than that.
I see.
You really take, I mean, if you want the enumerative definition,
Right.
Then you really think of HG of X as H of X. I should put the EG on the left. EG times G X.
Oh, I see.
So that's some infinite dimensional.
Oh, I see.
And then the counts, the intersections would take place there.
So it has no simple enumerative interpretation. This new number which you are defining.
Yeah, not the
Okay.
not the equivariant extension.
Okay. Okay. I see. Thanks.
This, and use the Poincare duals, right? So we can't do that in the equivariant setting.
Yeah, so the push forward would be over, you know, when you have the equivariant fundamental class, it gives you a way of pushing forward, but it's not using the Poincare pairing anymore. It's using the
It's not using the what anymore? I didn't hear you.
yeah, the push forwards in equivariant chromology are more complicated. You're basically working over H of BG everywhere, but then yeah, then it still makes sense to push forward. And I mean, another way of saying what you're doing here to define the quantum product, I'm really taking F0 star of the first class and F1 star of the second class. This is now a class in the homology of this thing, and then I'm pushing forward that class under the evaluation map at infinity. And that push forward uses the fundamental class on the moduli space. But this push forward definition also makes sense equivariant. Yeah, you have a sort of fundamental class in equivariant chromology, which you can use to define this.
Okay. Any more questions? Okay, so let's this again. So we'll see you again at the same time.
Okay, sounds good.
Yeah, and by the way, this gauge holomorphic maps and the vortex equations as moment maps, that we've been seeing it in some other courses as well. We lost the sound.
Oh, I'll go quickly through that next time and then, you know,
Oh, sure.
say
Okay.
what the applications are.
Okay. Okay, then see you tomorrow. Bye-bye.